Um, so welcome everyone to the GIST Sea Level Rise seminar. We're very glad to have Garrett Finucane. He's a physical oceanography graduate student in the UCLA Dynamical Oceanography group, and he is interested in ice shelf cavities, density, and inverse models. And today he will be speaking on the topic, the geostrophically constrained flow of warm subsurface waters into geometrically complex ice shelf cavities. So welcome. Okay.
Thank you. Let me try this screen share. Oh, amazing. Can you see that?
Yes.
Nice. Yeah. So, hey, everyone. My name is Garrett. I'm a third-year graduate student at UCLA, and my advisor is Andrew Stewart, who I did all this work with. And little fun fact, UCLA Dynamical Oceanography Group, UDOG. That's our moniker. Okay. So today I'm going to talk about some newish theory with a new metric that we call the hub. We're going to apply that theory in a suite of idealized models, and then we're going to test it in observations. And so all the work today is going to be focused on Antarctica. And this is no news to people in this call, but ice shelves across Antarctica are melting at really different rates. And we know that a large component of the melt is due to ocean-driven melting within the cavity. So hot water or just seawater in general getting underneath ice shelf cavities, making contact with the ice and driving melt. But what we don't yet have is a quantitative understanding of how different factors like geometry, surface forcing, offshore stratification, all translate to melt in general in geometries of any cavity, cavities of any geometry. And that's kind of a bummer because we know that meltwater and mass flux are really important, right? We know they contribute to sea level rise, even more so in the coming century, and that they are climatically important, that there's feedbacks between ice shelf melt and the climate around Antarctica and globally, as demonstrated by a recent paper out of GIST. So why don't we know about how ice shelf cavities work and the ocean circulation within them? And it's because ice shelf cavities have a lot going on. So there's sea ice, there's these katabatic winds that careen off the shelves that pull away the sea ice and can create polynyas, which create dense water. And all of this is happening in these like convoluted three-dimensional shaped cavities. And that makes it really hard to build like a mechanistic understanding of how cavities work. But one factor we know is really important is circumpolar deep water, which is this water mass that lies offshore, and it's warmer but saltier than surface waters. So it lies beneath surface waters in the Antarctic. And across Antarctica, it has different depths off the continental shelf. But we know that when it's able to get on the shelf and reach the ice, it can trigger really large amounts of melt. So there's been a lot of previous studies that explore the relationship between CDW inflows and bathymetry. Some of those have been on specific ice shelves or regions, in observations or in models, and some have been on idealized geometrically simple ice shelf cavities. So here is some studies on the regional side of things. I kind of just picked two that I like. One is this paper by De et al. In 2020, and they have this regional model that's supposed to be that's supposed to represent the filtration around, and they were trying to do a sensitivity study to figure out what it takes to trigger really high mass flux out of the ice shelf in the filtration around. Like, what do you have to change in the ocean to get really high melt? And they find that you need to shallow the thermocline, which means get the hot water higher, get it over the dominant bathymetric obstacle that blocks hot water offshore from reaching the ice. And two, you need to shut off dense water formations enough that you can let that hot water in to trigger melt. Another study looked at, by Nakayama et al. In 2019, it looked at Pine Island and Thwaites in a realistic regional model. And this study just showed that temporally and spatially, a lot of the melt that happens, at least in their model, is tied to when you have high CDW inflows, when and where you have high CDW inflows. There's been idealized studies, like I said before. One by Garrett et al. 2014 looked at this geometrically simple ice shelf cavity. I have a cross section of the geometry up there in the top right. So this is an idealized model. It has an ice shelf, and it's meant to be dimensionally similar to Pine Island. And they ran a bunch of experiments with different sill heights and different thermocline heights. And the main takeaway, at least for the interest of this talk, is that, again, the higher your thermocline, the higher your hot water, the more melt you have. And the last study I'll talk about in this context is this paper by Ken Zhao et al. In 2019. And Ken Zhao is actually a former lab member of Andrew, who just graduated 2 or 3 years ago. And he has this paper that is this idealized model of a fjord or a cavity. It's just a 2-layer model, and there's no ice. And so the way that he kind of mimics mimics there being ice is he prescribes this difference in the layer interface height between the northern boundary on the left and the southern boundary on the right. And that's something that you see in real ice shelf cavities due to melt processes, that the warm water is depressed towards the ice shelf face, towards the ice shelf face. And so what Ken finds is that in this 2-layer model, that change in interface height from north to south, it drives a geostrophic current in the along sill direction. So you have this north to south pressure gradient, basically, because of the change in layer interface. And that drives this flow along the sill that then hits the wall and gets directed into the southern part of the cavity, where if it was a fjord or if it was an ice shelf, we would expect there to be ice. And this kind of pattern of circulation is something we see in other idealized models of ice shelf cavities. So on the left, that's a plot of circulation in Ken's model in the lower layer. So that's like what we would think of like the warm water layer or like the CDW layer. And then on the right, we have a circulation figure from Garrett et al. Of the bottom velocity. So same kind of thing. And you see, again, this flow that goes along sill and then is redirected into the cavity along the cavity wall. And this figure that I put on the right is another one from Ken's paper, and it's a lot to take in. But all you really have to know is that on the y-axis, the values are the ratio of the transport into the cavity as diagnosed from his model, or divided by the geostrophic velocity you would imply from the change in interface height from the north to the southern boundary, which is a mouthful. But basically all this figure is showing is that you can predict or estimate the transport into the a cavity in this 2-layer simplified model just by calculating the along sill geostrophic transport. Cool. And so this is kind of the background for the work that me and Andrew have been doing. And it seemed really exciting, right? So in like the idealized studies, we have people saying that they have equations and relationships for the transport of CDW into like simplified idealized geometries. And then in the realistic world, we have modelers and observationalists saying that, oh, we know the transport of CDW is really important to basal melt. And so we were kind of looking to bridge that gap. And so our goal is to build a general understanding of the physics that drive warm water inflows and therefore melt in ice shells of any geometry. And and bring those two worlds together. And so to do that, we're going to imagine, kind of like Ken's paper, a 2-layer ice shelf cavity circulation, but this time we're going to include the ice shelf. And And so what I've drawn here is an ice shelf with like a lumpy sort of continental shelf and bed and some sill somewhere. And we have in red this CDW layer that comes in from offshore on the right. And then it's going to run just about flat until it hits the ice shelf face and is deflected down to the grounding line. And that's something we see in models and to some extent in observations. And that's because, where the CDW does make contact with the ice, it drives vigorous melt and a boundary layer forms. And so the CDW layer is deflected downwards. And so if the CDW interface follows that ice, we know that that is going to induce geostrophic velocity, like a thermal wind. And if we make the assumption that Ken holds, at least in his idealized model, that all of that geostrophic transport into and out of the page is going to be redirected into a boundary current, we are going to say that all of that transport into and out of the page is going to come in as a boundary current in the bottom layer and exit as melt, or the heat that it delivers will drive melt, and the freshwater flux from that will come out in a plume from the ice shelf. And so we can start to write some equations for that. So here we have the T, which represents the transport into and out of the page, the geostrophic, just the transport into and out of the page in our ice shelf cavity. And here we just have the integral as we go from left to right of the speed into and out of the page, or velocity into and out of the page, times the layer thickness at any point. And then we're going to use the thermal wind equations to approximate that UCDW term. And then we're going to say, well, SCDW, the slope of the CDW interface, we're saying that when that hits the ice, it follows the ice. So the slope of that interface is really kind of like the slope of the ice itself. So we're going to replace that SCDW term with an S ice term, slope of the ice. And we're going to say, the integral of the layer thickness across the cavity, that kind of goes like the thickness of CDW at the entrance to the cavity times the length of the cavity. And at this point, we've dispensed with being precise at all. And so all of those equal signs have become tildes. So it's really a scaling argument. It's a scaling argument for the transport of that CDW layer into the ice shelf cavity. But out of all those terms, maybe a lot of them look familiar, right? Like, G in prime, stratification, whatever, Coriolis parameter, there's no problem, length. But the thickness of CDW is hard to quantify, especially in complex 3D geometries. And so we came up with this thing that we call the highest unconnected isoBath, which is going to help us calculate that layer thickness. And the highest unconnected isoBath is the shallowest depth for each point on the continental shelf, at which that point is unconnected to the open ocean on an isosurface of depth, which is a really hard definition to wrap your head around. So I'm going to walk us through it in 2D and then in 3D. So then in 2D, the hub is pretty easy to figure out, and it's what we'd expect. So if we want to find the hub for this green point, we're going to say, okay, is this point connected to the open ocean, the right side of the page, on an isosurface of depth? It's not. So what we're going to do is we're going to scan upwards. So we'll move that green line a little higher. It's still not connected to the open ocean, and a little higher. If we were to go any higher at this point, we'd be connected to the open ocean. And so that green line right there is the hub for that green point. And that, in 2D, it's really easy to see as either, what we just usually call the sill depth, or the maximum height of the bathymetry between any point and the open ocean. In 3D, I made a little diorama to help us visualize this. So this clay mold is kind of like an ice shelf cavity bed if you squint. And the top left represents our grounding line. And we're going to imagine that our hypothetical ice shelf cavity has been completely emptied of water, and we're going to pour in hot water from the outside. Well, it could be cold water too, I guess. And the hub is going to be how the depth at which that water needs to be poured to reach any point on the continental shelf. So these two black points, they're the same elevation, but because there's a sill on the right-hand side, the 2 points have drastically different hubs. Yeah, and so the hub's nice because what it really gets at is for any point on the continental shelf, it tells us how high hot water needs to get offshore in order to reach that point. And by the same token, we can just we can look at the height of CDW and subtract from that the hub to get our CDW layer thickness. And it's really easy to calculate. All you need is some bathymetry and some ice data, and it takes under 5 minutes for all of Bed Machine 2, which has Antarctica's bathymetry at 500-meter resolution. Excuse me. And it has a rigorous topological definition, so it feels like we know what's going on with it. Okay, so we took a little detour to figure out HCDW, but we're back to this equation, which is our scaling argument for the transport of the CDW layer into the cavity. And we don't, the transport into the cavity is cool, but ultimately what we care about here is melt. And so what we're going to do is we're going to make this assumption that all of that, the heat transported in by that CDW layer is going to be used for melt. So on the left-hand side, you have area average basal melt times, width, length, the usual characters to get you to heat flux. And then on the right-hand side, you have transport into the cavity, the change in temperature between your surface and your CDW layer. And still there's that tilde there because we're saying that, this is still kind of a scaling argument, who knows what T is really. And yeah, just a reminder of what T was from the slide before. And we're going to take that expression we had for T and we're going to plop it in. We're going to plop it in, and then we're going to move everything over and solve for m dot, which is our predicted melt. And we're going to define our predicted melt as everything we had on that we moved over to that right-hand side. And we're going to get rid of that tilde and add an inequality and put in some non-dimensional scaling parameter. And so all we're saying is that, all that transport from that scaling argument that we just talked about, that's going to be used for melt. Up to some, coefficient. Who knows? It's worthwhile to take a moment to talk about how this is really different than existing approaches to parameterizations of ice shelf melt. So here we're trying to guess melt based only on the transport of heat into the cavity. So you can imagine we don't care about anything that happens inside of the cavity, and we're not even trying to guess it. All we're saying is that the heat transported into the cavity by this boundary current, that heat's going to be used up for melt, and we're going to see melt water come out in the top layer. And that's really different from traditional parameterizations that try to guess or try to figure out what the temperature of the water is at the ice-ocean interface and solve for the melt there. So a lot of traditional parameterizations, there's T squared times slope or T times slope. There's a number of them. So we're kind of just ignoring the ice. It's a very oceanographer's approach to ice shelf melt. And that means we don't get any spatially varying maps of melt for individual ice shelves. So we're not solving for the melt at each point on the ice shelf face. We're just trying to basically guess the heat transport into the cavity and what amount of melt that results in. Cool. So we have an equation. We'd like to test it out. So we decided to spin up a series of idealized models. So we have this MIT GCM model, and it's really kind of constrained. So it's really just the ice shelf cavity. And then we prescribe the temperature and the salinity on all the side boundaries. So offshore. So the cavity itself is left to evolve freely. And to do so, it has a 2 kilometer resolution in the horizontal and a 2 to 20 meter resolution in the vertical. And the nice part about this is it runs fast. So we can run a lot of experiments. So we're going to try a bunch of different cavity geometries with a bunch of different forcing regimes, and we're going to see what happens. So I'm about to put up a lot of dots onto the left-hand side of this page. So this plot, the y-axis is melt rate per year. The x-axis is thermocline height. And every scatter point on this plot represents a 10-year simulation of one of these cavities. And each color symbol pair represents a unique cavity geometry. So these 3 orange circles, each of those has the same cavity geometry and just different prescribed thermocline heights offshore. And so you can see the relationship we'd expect, that the higher the thermocline, the higher the melt. And so here, these circles represent different shelf widths. So in gray, we have a really wide cavity. In purple, we have a medium cavity. And then in orange, we have a really narrow cavity. And as we go through, you'll see that we're also prescribing different randomized perturbations on the bathymetry as well. So we're trying to make it look lumpy and as close to, reality as possible. So yeah, we have different shelf widths. We have different shelf depths that vary from, in red, pretty deep shelf, to in orange, something I always think it looks like a clarinet reed, or I don't know, not specifically a clarinet, but just like a reed, but very thin. And then we have different ice front distances. So in orange, there's one that's pretty recessed, and in gray, there's one that almost spans the whole domain. We have shelves with a more prograde slope, so mimicking almost as if there is no sill. Different cavity depths. Before I said different shelf depths. The difference there isn't that important, and maybe I should have combined them. But the point is all these different geometries, randomized bathymetries, and you get this plot. And like I said before, it's kind of what you'd expect. Higher the hot water, higher the melt generally, but it's pretty scattered. Okay. Before we go forward and apply the equation, there's one more modification we're going to make, and that's to try to get rid of this width term. So length and width of ice shelf cavities in general are really awful parameters to have if you ever want to apply something to a real cavity. And that's because in the real ocean, in real ice shelf cavities, length and width are not clearly defined and pretty amorphous. Is that a width? Is that a length? Who knows? And so you may not have noticed, but through sleight of hand, we already got rid of length. So we had a length on the left-hand side in our scaling, in our melt term, and then we had a length on the right-hand side in our scaling argument for transport, and those canceled out. But getting rid of width is a little trickier, and it actually comes from an observation that we made in our models, which is that the stratification inside of the cavity varied in such a way that the added ice shelf area was balanced by a stronger geostrophic flow in the cavity. So basically, the wider you made your cavity, the stronger the stratification inside of it got, and that meant more hot water in, which balanced the more ice you had to melt. I explained that a little poorly, but basically what it allows us to do is to replace the interior stratification of the cavity divided by the width, which was a term in our equation for melt, replace it with the stratification outside the cavity divided by some constant W0. And this idea of ignoring width isn't completely novel. So on the left, those are our model experiments where we varied width. You can remember gray was the widest, orange was the narrowest, and there's not much different in melt for models with the same thermocline depth. And then on the right, I have this paper from Christopher Little et al. In 2009 that has that looked at melt in idealized cavity geometries, and the rhombuses and the squares are the same cavity geometry, except they have different widths, and you can see the melt is basically the same. So it feels weird to just like get rid of width, but hey, maybe other people agree. And so we have that G prime and that W term hanging around in our equation. And so we can just swap that out with the exterior stratification, the stratification outside of the cavity, divided by some constant W0. And that's really nice because if you look at this equation now, nothing here requires knowing anything about the inside of the cavity. We can calculate all of these things just from the hydrography offshore. So yeah, we're going to do one more task, and we're going to take all these constants and we're just going to lump them into one big constant that we call C. And yeah, C contains alpha. So we're going to need to, which is our tuning parameter. So we're going to need to regress to find it. But everything else we can calculate using the offshore hydrography. Cool. Okay, so we have this equation and we want to apply it to our idealized model. So what we're going to do is for each cavity, we're going to take the temperature profile we prescribe from offshore, and we're going to calculate that temperature term by taking the temperature at the hub depth. We're going to call that our CDW temperature, even if it's a bit of a bad name because maybe there's not CDW there. But we're going to take the temperature at the hub depth, and we're going to subtract from that the temperature at the surface, which is always going to be just around freezing. And that'll be our temperature term. Then we can find the picnic line and subtract from that the hub depth to get our layer thickness HCW. We can estimate our G prime by taking the reduced gravity above and below the picnic line. The ice shelf face, the ice shelf slope in our model is really trivial to diagnose because our ice shelf face, as we prescribe it in our model, is flat. So it's just, length, depth over length. Easy to calculate. And then, yeah, like I said before, we're going to linearly regress to find C because our tuning parameter's in there. And the key point is that we're going to choose one C or one alpha for every ice shelf. So we're not tuning per ice shelf. We're going to, we're picking one value for all the ice shelves. Great. So we linearly regress and we apply our equation and we get this pretty nice looking line. So on the x-axis, we have the melt as predicted by our scaling argument, our parameterization. And on the y-axis, you have the melt as diagnosed from the model. And that looks pretty good. You can see there's some variations around the line as you'd expect, but one of the things that's nice to see is that models with the same cavity geometry, so with the same color symbol pair, even as you change the thermocline height and the melt changes, they fall along pretty linear lines. So yeah, something nice is going on here. But it's just an idealized model, and we wanted to try it out in observations. So what we did is we're going to take this same scaling argument, and we're going to use bed machine bathymetric data, bed machine 2 bathymetric data. We're going to use World Ocean Atlas hydrographic data. It's like a gridded hydrography data set. It's like decadally average temperature and salinity depth profiles. And we're only going to use World Ocean Atlas data from the 1,500 meter isoBath, so pretty far offshore. Definitely not on the shelf. And then we're going to try to use those. We're going to apply our theory, and we're going to try to guess satellite-derived melt from Adusumilli et al. 2020. And we're going to try to guess basal melt rate, area average basal melt rate. Cool. So the first thing we're going to do is we're going to calculate the hub for all of Antarctica. So there's the bed machine 2 bathymetric data for Antarctica. And we're going to calculate the hub. And it looks really boring. And you might be saying, well, don't be so hard on yourself. It's just a bad color map. But even with a different color map, it's still boring. And that's because what the hub is doing is it's finding, like I said, the deepest depth that water is able, the deepest depth water can be and still make it on to the continental shelf. And what that kind of amounts to is a simplification, in that when you have these sills across Antarctica, all the points on a continental shelf that are behind the same sill are going to have the same hub. So you get these big connected regions with the same value. So the best color map to pull out what makes the hub cool is a random one. And so when you apply a random color map, these blobs kind of pop out at you. It's like a Rorschach test. It's kind of psychedelic. And you can see these big regions on the Antarctic continental shelf where CDW or offshore waters are all blocked by the same bathymetric obstacle or sill. So up there, I have the Filchner-Ronne, the Amundsen, the Ross, the Totten, the Moscow, and the Amory. And if you've looked at these ice shelves bathymetries before, you might see like familiar kind of shapes. The Filchner-Ronne in particular, you can see that the snout or this like a feature up here, if you were to go any higher, that's the Filchner trough. So yeah, the hub captures these dominant bathymetric obstacles. Cool. So we have the hub for all of Antarctica. So that's great. And we have our equation. And we want to apply our equation. And the way we're going to do that is we're going to take every grounding line point in bed machine 2 in Antarctica, and we're going to calculate these terms I've outlined in purple, those hydrographic terms. Well, F isn't really hydrographic, but it's easy to calculate, I guess. And so in the model, it was really easy to do this because we prescribed the temperature and salinity. So there's only one forcing profile that you could feasibly even choose. But to find the closest hydrographic cast on the 1500 meter isoBath for a grounding line point in Antarctica is surprisingly hard. If you just do it, if you just did like the closest point by distance to some grounding line point on the 1500 meter isoBath, you can run into problems really quick. So here's the West Antarctic Peninsula, and the closest point on the 1500 meter isoBath is on the other side of the peninsula, which obviously isn't where we think these CDW inflows, if they exist, would be coming from. So that's not what we want. And so what we want isn't the closest as like the crow flies, but more like the closest as the CDW could flow. And so for that, we're going to do this kind of convoluted search outward from the grounding line to the 1500 meter isoBath. And what we're going to do is we're going to restrict that search to the set of depths that is just that is below, just above the hub. And that I recognize is a mouthful. And basically, if you think about how the hub is the highest depth at which a grounding line point is disconnected to the open ocean, then just above it is the deepest depth that it is connected. And so here to illustrate that, maybe make it a little bit clearer, I have the Filchner-Ronne, and I have two isoBaths. And if we wanted to know, the hub for some point on the grounding line in the bottom left corner, it would be this green contour here, because that green contour is closed. So at that depth, the grounding line points are disconnected from the open ocean. But just 5 meters above that is the red isoBath, where suddenly there's a connection to the open ocean. And so what we're going to do is we're going to search within that red isoBath to find the closest point. And so I've illustrated that here. So we have the 1500 meter isoBath offshore. It's that red line. We got a red point in the bottom left. That's our grounding line point. And this blue area is, that kind of all the points deeper than that red isoBath. Below, just above the hub, which I admit is confusing. And so then we're going to search outwards until we hit the 1500 meter isoBath. And then that's the hydrographic profile that we're going to use to calculate our scaling argument. And just to be balanced, because I bragged about how fast the hub is to calculate, this process is like extremely slow. It takes me like a week on my desktop using all 8 cores. So, if I used a bigger computer, I could make it faster. But it's a big pain. But the nice thing is you only have to do it once for any grid. So that's some consolation. So we've gone through that process to pick a hydrographic cast. And I think of it kind of like watersheds, So if you're, this is Los Angeles. If you're at 2 points in Los Angeles and you dump out 2 cups of water right next to each other, they could flow to completely different bays in, Santa Monica Basin, or, down to Long Beach. Yeah, down to Long Beach. But, and I think that's kind of similar to grounding line points in Antarctica, where you can have 2 points that are next to each other, but because of bathymetric features in between them, they could be sourcing CDW from really different points offshore. So that's kind of the analogy that I think of. And then from there, the process looks really similar to what we did for our models. So we take the thermal term, we take the temperature at the depth of the hub, we estimate the picnic line and subtract from that the hub depth to get the layer thickness. We estimate the stratification above and below the picnic line. And Coriolis parameter, as always, it's pretty easy to calculate. And then we take the predicted melt, the observed melt that we're going to compare to. We're just taking that from the supplementary table in the back of Adusumilli et al. 2020. So we're not even doing any calculations on that, just copying and pasting from a PDF. And then to calculate the ice shelf slope, we're going to take bed machine 2 data, and we're going to take the thickness of the ice shelf at any point, or depth, sorry. And we're going to take that, we're going to smooth it, we're going to calculate the ice shelf gradient, and then we're going to take the mean or the median of all that. And that seems a little arbitrary, and admittedly it kind of is, but what we really want is this like bulk metric of the ice shelf slope across the whole entire cavity. We don't care about the ice shelf slope at any particular point, like you see in other melt parameterizations. Like if you think about t-squared times slope, that's really getting at the importance of slope, which it definitely is really important on really small scales to like the efficient, like how well your plume can melt the ice. But this is looking at like the large scale slope for the whole entire shelf to get at this geostrophic, this change in interface depth that drives the geostrophic flow, that pushes hot water in and drives melt. So it's this bulk, simple metric. So I said we calculated all those terms for each grounding line point. We're going to average all the grounding line points by shelf, by each shelf they belong to. And then we can just multiply everything together, and we're going to linearly regress to find C. Whatever C is, the same value for every ice shelf. And when we do that, we get this scatter plot. And it looks pretty good. There's this pile up in the bottom left we're going to talk about in a second, but in these hot shelves that I've put in red, there seems to be this pretty nice relationship between the predicted melt on the x-axis and the observed melt on the y-axis. And to our knowledge, this is kind of the first time that people have, that we've seen at least, people compare or estimate observed satellite-derived melt from offshore hydrography without tuning for every shelf. So we're applying this simple parameterization, and from hydrography at the 1,500 meter isoBath, we're doing pretty okay at guessing melt. And so in the days preparing for this talk, I was like, oh no, these people, they don't care about area average melt rate. They're sea level rise people. They care about mass loss. And I had never looked at mass loss. So I was like, oh, I gotta calculate mass loss, but I'm nervous it'll be bad. And so I just took these and I multiplied them by area and the requisite constants to get to gigatons per year. And it looks like this. And it's not so bad. It actually looks pretty good. And if we go through and we add up every shelf to get the gigatons per year that the scaling argument predicts, we get about 1,467 gigatons per year. And Adusumilli et al., they get 1,265 plus or minus 150. So yeah, we're just on the upper end of that prediction, or of that estimate. And we're not when we make this switch to mass loss, we're not fitting. We're just using the exact same predictions for melt for the area average basal melt, and we're just multiplying by area. So yeah, no difference between those two charts except we're multiplying by area on both. Yeah, and that's exciting and pretty wild given the extreme diversity of ice shelf cavities, right? I opened this by saying that there's all these things going on in ice shelf cavities, and we ignored them. And the question to me, at least, was maybe that's all baloney, and this is just some like weird statistical thing that I've managed to draw out of the data. And it definitely, I don't think it is. And that's because, well, we saw it work pretty well in the models, and so that's heartening. And yeah, the data we're using is simple, coarse, and uncorrelated, right? We're using this decadally average temperature and decadally average satellite derived estimates, and we're seeing this pretty nice relationship. That's cool. But I included a grain of salt. And also the model and the observations, they show similar kind of structure. So in the top left, I have the observation, I have each ice shelf from the observations with the observed melt rate on the y-axis, and on the x-axis, the thermal term. And then in the bottom right, I have the diagnosed melt rate from the models on the y-axis and the thermal term on the x-axis. And you get this weird kind of like curvy exponential thing going on. And then you multiply by the thickness term and your stratification term. And things start to become a little more fan-like, and then you multiply by slope, and things pull together a little bit. So yeah, still hand wavy, but it's heartening that they look similar as you build up this scaling argument. And if that's going on, if this geostrophic transport is really what dominates the melt in these cavities, there's a lot of interesting questions to ask, we think. One of them is that one of the terms in our scaling argument is not like the other. The ice shelf slope. We had all these hydrographic terms, and then we had slope. And this dependence on slope says something really interesting about the susceptibility of ice shelves to increased melt with increased thermal forcing, right? So if you look at this graph, which has ice shelf slope on the y-axis and the hydrographic terms on the x-axis, and then colored in the background is what our scaling argument predicts the melt would be. And you can see like shelves like Totten and Crossen, if you change their temperature even a little bit, because they have such high slopes, you expect to see really enhanced melt. But for shelves like the Ross, the Filchner, the Rhone, the Wilkins, they have such low slopes that even as you increase the temperature, we wouldn't actually expect to see drastic increases in area averaged basal melt. And so that's kind of a new thing to think about when we're looking at these cavities, if the scaling argument's to be believed. Yeah, and so I alluded to this pile up in the bottom left, and I'm going to try to convince you that this is actually a feature of our scaling argument. What's going on in the bottom left? It's this big mess. And first of all, the error bars are pretty big. So, that doesn't help. But really, all of our whole entire scaling argument was predicated on the idea that there was CDW access to this cavity and that we're going to predict its transport. But a lot of these cavities, they just really have no CDW. So this big mess in the bottom left corner is our scaling argument kind of throwing up its hands and saying, like, there's no CDW. What do you want me to do? It's cold. And so the useful part of that is that it actually ends up being a pretty nice way to go around Antarctica and say, is this a hot cavity in that it has vigorous transport of CDW, or is it a cold cavity where we think some other processes are going on? But even though, yeah, it's nice that it does that, we would like to figure out those cold shelves, because even though they have really low area average basal melts and the error bars are big, they contribute a lot to sea level rise and meltwater flux because they're so big. Like the Filchner, the Ross, and the Rhone, they have huge areas. So even though they have low area average melts, they have high mass fluxes. And so we'd like to do better at predicting them. And so, yeah, just following on from that, one of the things we want to do next is we kind of want to take this same methodology of bouncing back and forth between idealized models and observations to figure out how we can better predict melt in cold shelves. And so this is what I'm most excited about recently. This is observed melt on the y-axis, again from Adussimile et al. 2020. And on the x-axis, we have grounding line elevation. And I've scattered and labeled every ice shelf in that data set. And now all I'm going to do is I'm going to say, if our scaling argument predicts you have more than 5 meters per year of melt, if you're a hot cavity, we're going to ignore you. And so this is the exact same plot, but we've gotten rid of everything that our scaling argument says is a hot cavity. So this is only the cold cavities, but still with observed melt on the left, on the y-axis, and grounding line elevation on the x-axis. And you can see, like, who knows, maybe it's baloney, but it looks like there's this interesting relationship between grounding line elevation and melt. And that's something we'd love to test in idealized models like we did with hot cavities. So that's exciting to us. Another thing we'd really like to do is try this out as a model parameterization. These geostrophic flows that are getting redirected as boundary currents, the prospect of resolving those in GCMs is actually pretty bleak because these boundary currents are, 10 kilometers or less. But maybe we could make a parameterization to help with that. And the question is, how can we take these same lessons we've learned about the importance of geostrophic transport and apply that now as a model parameterization with a bunch more knowledge about the domain, right? Because with the observations, we're using this coarse data from the 1500 meter isoBath, but when we move to the model, there's all this exciting stuff we could try to do. We could, try to use what's going on with the shelf. Maybe that's a good idea. Maybe it's not, but there's all these new things we could try because we have a whole wealth of data in a model that we don't have in the observations. Yeah. There's a bunch of other things we'd like to explore, like how does our scaling argument do on shorter timescales, right? Like how well does it predict melt as you have your thermocline rising over some time? What does it tell us about tipping points? And when I say tipping points, I just mean, what does it tell us about triggering this rapid onset or these really high area average basal melt? And that kind of gets that whole slope thing I was talking about before. And what does it mean for melt in a warming climate where we expect temperatures to rise and maybe we expect CDW to rise and we expect the stratification to change and the slope of ice shelves to change. So all those terms in our scaling argument are changing in a warming climate, and it would be interesting to know how those all contribute to future melt. Yeah, so just to wrap it all up, we think that the hub can be a helpful metric for determining the height of available CDW across the Antarctic continental shelf, and that by approximating the geostrophic flow due to the geostrophic flow inside of ice shelf cavities, we can better predict the heat transport into them and therefore the basal melt. And that this scaling argument we came up with shows skill in predicting area average melt and total mass flux. But there's a lot of room to improve for sure. Yeah, that's all I got.
Okay, thanks a lot, Garrett. That was great. Do we have any questions?
Yeah, I have a question.
Hello.
Hey, Garrett. Long time no see. Big fan.
Yeah.
So yeah, I don't do sea ice stuff or oceanography stuff, but I was curious what you said about how this method doesn't capture the spatial component of melt, and I'm curious, like, kind of if you could give me kind of a rundown of why the spatial component is important, and then also like if you have any plans to kind of, because I think you mentioned like you could use this as a model parameter, like could you kind of use like your number of melts that you've gotten as a constraint and then try to get some spatial stuff, or are you not really going to touch the spatial stuff? So yeah, that's my question.
Yeah, that's a great question. Thank you. Yeah, so the importance of the spatial component of melt is there's a lot of different important parts to it. One that you can just kind of see from our equation is that the slope of the ice shelf is really important, right? And so you can imagine you can like quickly change the slope of the ice shelf by like melting different parts of it at different speeds. And also that by changing the various patterns of melt, they can lead to different instabilities in the ice. There's a whole wealth of ice research stuff going on. I think the prospect of us getting to I don't think we'll be doing any spatially varying melt stuff because we're ocean people first and foremost. But there's a lot of really, really cool work that does a really good job of doing the spatial melt work. Like there's a cool paper on this model called LADDI, which is a fun name. But yeah, in terms of using it as a constraint for models, yeah, I was wondering the same thing myself. I feel like I don't know enough about ice shelf modeling. But, as it stands, my understanding is that a lot of GCMs that we have, they don't have ice shelves at all because online, like there's not like this interactive feedback between the ocean and ice. So there's like a lot of room to improve there, I guess is what I can say. Yeah, thanks.
Cool, thanks. Yeah. Also, that random color map was a cool thing. Really sick.
Thanks.
Any other questions?
Hey, this is Letty.
Hello.
Really nice talk. Thank you. You mentioned, so you did mention about other parameterizations. And I was wondering if you had thoughts about how you might compare this to other things. So I'm thinking, I guess, a bit about so we're starting to use the PISM ice sheet model, and that has the PICO box model for ice-ocean interactions. And so I wondered if you thought about looking at how this compares to something you might get from that.
Yeah, I've never run PICO myself. To our knowledge, no one's really ran PICO on like real ice shelf, like using observations to try to estimate melt.
Mm-hmm.
We could certainly go in and try running PICO using these same hydrographic estimates. I think she was actually formerly a speaker here, but Clara Burgard.
Yes. Yeah.
She has a really fantastic paper that I think she talked about actually called An Assessment of Basal Melt Parameterizations. And in it, she finds that PICO performs, I think, less well than a simple quadratic dependence times of ice shelf melt on temperature times slope. Like PICO does less well at producing the melt there. So I'm in terms of comparing, we've done some comparisons to T-squared and slope and stuff, but it gets into a little bit of a weird territory because we calculate the way we calculate all this stuff is using the grounding line points because we're trying to capture basically fit the real life observations into our like cross-sectional 2-dimensional 2-layer model of an ice shelf. But when in Clara's work, for example, they don't calculate it for just the grounding line, they calculate it for the whole entire ice shelf face. We have done experiments, it was now like quite a while ago, where we did T-squared times slope along the ice shelf face, and we find that you don't get as good of a prediction. In fact, we worked with Clara. So Clara, I don't know, maybe you got the sense from the talk, like the kindest person ever. And I reached out to her.
I know Clara. Yeah, Clara's great.
Yeah, so I just reached out to Clara and I was like, oh, I got this thing called the hub. Could we try it out? And she was like, yeah, no problem. And that was amazing. And so we actually plugged the hub into, sorry, let me go for it to find it. This is a data from Clara. So we plugged the hub into her assessment, that the code from that paper, and we found that using the hub drastically reduced the error in the melt rate using T-squared times slope for the biggest ice shelves, which I can get into why that is maybe another time. But it didn't actually end up doing much better for all the shelves across Antarctica. I'm trying to think. I think I have a plot here.
Wait, sorry. Say that again. It did better.
It did better in a certain few really big shelves, and basically, that's not using our parameterization. That's using just the hub. So it's not really a great comparison. Although again, there's all these layers of confusingness because in Clara's model, I'm not sure that they would actually be able to resolve the boundary layer, the boundary currents that we think are transporting hot water in. So even using our parameterization in those models probably won't do well because the melting might be happening through a completely different process. Yeah.
Right.
I'm trying. I think. Oh yeah. So this is just t squared at the grounding line. So this is using that observational, the observed melt rate on the y-axis, and then on the x-axis, it's just the, it's just t squared. Yeah, and you get not a very good relationship. But to be fair, this is not the best comparison to t squared, like a traditional t squared parameterization, because we're doing it at the grounding line and not at the ice shelf face. So, yeah. Sorry, that was a scatterbrained answer, but yeah.
So do you need a coupled module, or could you just diagnose melt rates based on some very high resolution, some other thing, you know, higher resolution than what Clara has? And would you then be able to compare some of the other kind of parameterizations available and, you know, that are used in the community to yours? Because it would be really nice to see like a good like for like comparison, I think.
Yeah. Yeah, I think we could do it. Yeah, we could. Yeah, I don't think we would need an ice shelf for sure. Just something that was, yeah, much like our idealized model that you know that like it wouldn't need to be coupled, like the ice shelf wouldn't need to be.
Right, it doesn't need to evolve.
Yeah, it doesn't need to evolve, but yeah, we could compare it to t squared and Pico and those existing parameterizations. Yeah.
Cool, thanks.
Thank you for the question.
Any more questions?
Hi, Garrett. This is Damien.
Hello.
Hi. I had a question about the step where you said it takes a long time to compute.
Yeah.
Like if I imagine that I have a coupled model with like coupled ice sheet and ocean model, did I understand right that you would need to redo this if the grounding lines change positions?
Yeah, you would, although it's a bit, I think you could get pretty clever with it just because, you know, this bed machine 2 data, it's at 500-meter resolution. And that's part of the reason that the searching takes so long. I think that in a more coarsely resolved model, you could drastically reduce the time, and you could also get pretty clever about how you do it such that it was a bit faster, I think.
I see.
Yeah.
I see. And I guess it doesn't change, like if it doesn't change a lot, it should not change a lot with your results as well.
Yeah. I think there's even, I think if we spend some time with like pen and paper, I think you don't even need to recalculate if the point is getting deeper or something like that. Yeah.
Yeah, I see. Yeah. Oh, okay, thanks.
No problem.
Any other questions? We're a little past the hour, so I guess we could stop there. So yeah, thanks again, Garrett.
Thanks for having me.
And Happy New Year, everyone.
Yeah.
Happy holidays. Thanks, Patrick, for organizing.
Thanks, Garrett.